test will cover, but we are going to go over the things that it really focuses on. And in the past, what I've had you guys do is kind of solve the problems that I've put on the board. Today, because we only have an hour, I'm just going to do them, but sort of talk you through how we do all of these, okay? So what I hope is that as we're starting to do these, you guys will realize, like maybe a little light will go off, like, oh, I forgot how to do those, or okay, I see how this is working. But I don't have a lot of time to just sit and let you guys solve it and really kind of marinate the problem. So try to stay with me and do pull out a calculator and stuff. So if I do say like hurry and calculate what this is, you can kind of participate like that. To start off, what I want to go over is the periodic trends. What's awesome about Chem 105, what you guys are probably noticing when you get to the end, you look back and you realize, wow, I've learned a lot and I can answer a lot of questions about simple things in chemistry. Meaning, if you put up a balanced equation, right, there is so many things that you could determine about that equation. You could look at all the reactants, try to draw their Lewis structures, figure out how many lone pairs they have, what is the hybridization around those Lewis structures, how many sigma and pi bonds. You can determine if those things are polar, non-polar, what are their intermolecular forces. So you're noticing you could write an entire final off of just one chemical reaction, just asking tons of questions like that about those species. So part of the things some of the important things you need to remember are the little things that help you answer the bigger questions. So one of the things I want to bring to your attention again is the periodic trends. Remember the first of the semester we worked on the periodic table, kind of got familiar with it, and tried to figure out what are the trends that we normally see. Well, the big one that's probably talked about the most in chemistry that you'll see also in Chem 106 and in OChem is when we talk about electronegativity, because it really affects compounds, electronegative elements, right? So the electronegativity pattern goes to the right of the periodic table and up. So what does that mean? It means as I shift as I'm trying to pick elements that are more to the right and up on the periodic table, they become more electronegative. And what electronegative means is that element or that atom will really influence the electrons of its neighbors, right? And not even just its immediate neighbors, its neighbors in the entire molecule, right? Because that atom just has a way of wanting to draw in the electrons. It has its own electrons that it pulls tightly, but beyond that, it's trying to pull on the electrons around it. And that is really important because as we start to add electronegative elements to compounds, those compounds turn a little bit more polar, especially if you don't have a symmetrical way of placing them. So, following the same pattern of electronegativity is electron affinity. And I remember at the first semester, this was something that we were getting confused quite a bit. And it can be confusing, but they do describe different things. What we just said about electronegativity is that the atom is pulling on the electrons of the neighbors. Electron affinity is how tightly that atom is holding its own electrons. So it makes sense that that trend would follow the same pattern. So when they say something like fluorine is the most electronegative element on the periodic table, which is true, we also know that it has a very high electron affinity, or a love or care for the electrons that it has. So it makes sense that it would be extremely difficult to take one of fluorine's electrons. When's the last time you guys did a problem and you saw them talk about a cation F+? Never seen it, right? We just see F-. That's because it's just too hard to take an electron from fluorine because it's small. It has 9 protons in its nucleus, and so it's really able to pull on its own electrons and hold them tight. These types of ideas are important for answering these questions, understanding what it might physically look like, and therefore why does the chemistry occur, okay? So, an opposite trend, and it's the only trend that we're really following that's opposite, is atomic size. So far, electron affinity and electronegativity go to the right and up. Atomic size goes down and to the left. And this is important because this tells us a lot about things like ionization energy and how something might react. So if I'm an atom and I have a ton of electrons, if my electron cloud is really big, right, that means that my nucleus is pretty far away from my outer electrons. and therefore it can't pull on those electrons very hard, which means those electrons can be easily taken from you, right? Easily stolen. So as we move down and to the left, the size of our atoms get bigger. And it's not really because we're getting more protons, because we actually gain more protons as we go to the right. So if we were thinking that it was protons, we might say something like chlorine is quite a bit bigger than phosphorus, right? It's 2 more protons. But what's really happening is those protons are just pulling on the cloud even harder, so it actually draws the cloud in, right? So as I lose more protons, but I have really far out valence electrons, they're just not held as tightly, and my atom gets bigger, okay? And that's important, again, because as the atom gets bigger, I can easily lose my valence electrons. So let me ask a small quiz for everybody. Which one would have a higher ionization energy, which means it would take more energy to steal its outer electron? Sodium or rubidium? So 11 or 37? Sodium, exactly. Because it's a little bit smaller and its protons can hold the electron cloud in a little bit tighter.
So how does hydrogen, since hydrogen is as far left as you can go with?
So hydrogen is it's kind of an exception, and it's something. It's usually they don't talk about hydrogen a lot in terms of is it electronegative and stuff, because that's why some periodic tables you'll see it clear to the right over here by helium, or to the left. So hydrogen kind of acts as its own thing because it's just one proton. So it's not. We don't really talk about it as much in terms of trying to compare it to other things. Okay, so that's the periodic trends, and a lot of questions can come from that, okay? So, let's start here on the right with electron configurations. Nobody really liked electron configurations, but it will be on your test. This was one that was highlighted in red. It will be on your test. So, I picked one right here, MO, right? I specifically picked this one because this is one of those elements that doesn't follow the rule. It's one of those exceptions to electron configuration. You guys remember, electron configuration normally is pretty easy. You literally just look at where the atom is in the periodic table, and you start reading backwards what electrons are there. The hardest part about electron configuration is just remembering, we have our S columns, our D, and then our P. And they don't follow the same shell number, meaning where it starts at 4s, once I get to element 21, it starts at 3d. You guys have done a lot of problems like that, just to remind you. Okay, that's the most difficult part. But sometimes we get these elements, and depending on where they fall in the periodic table, theirs will be a little bit different. You guys remember, in the D shell, right, in the 3d, if we start with 3d, so element 21 and over, there's our 3d. There are 5 possible d orbitals. How many electrons per orbital? 2, right? So overall there are 10 electrons possible in these orbitals. That's why it's 10 spaces along, okay? If we take something that's what I would call this number 4 column in the d orbital, so starting with chromium right there, they do something a little bit special. Because they can only almost half fill their d orbitals, right? Because there are 4 electrons. So there are 5 options. It puts 4 in. They're all unpaired, right? But it has its 4s level is completely filled. So imagine its 4s level is here, its 3d level is here, but it's completely filled its outer electrons and paired them. But all of its electrons in the d's are unpaired, and I have a completely empty orbital. So everything in nature wants to follow this path of least resistance, something that makes it more stable. So it doesn't make a lot of sense to have your outermost level completely awesome and fine and full, and then this inner level kind of screwed up. I have gaps, I have spaces. So what it does is it just takes one from its 4s and drops it back into the d, right? So that I can half fill all of the d orbitals and have at least half filled, no completely empty orbitals in the d level, and the s level now is the one that I took an electron from. So when I do this electron configuration and I want it in shorthand, which means I don't have to write out all the electrons it has, I just find MO at 42, I take myself back to RB, and then to the start over here, and I see that I start with the first noble gas, okay, which is KR. So I come over, I write the brackets, got to figure out what is the electron. I'm going to name them off. So we knew that in the 5s, it actually took one of those and dropped it into this 4d. So I only have 5s1. I don't have 5s2 anymore. But I should have 4d5. Okay? So I just wanted to do this one so you can see all of them in the 4-column follow that pattern, and everything in the 9-column follows that same pattern, okay? So if it can completely fill the d orbitals or half fill it, that's how it will do it, okay? Let me think if there's any other questions that I can think of. Oh, you guys remember what the term isoelectronic means, right? Isoelectronic is when I take two different elements, and because one of them lost or gained electrons, when I wrote their electron configurations out, it's the exact same, right? So there are a couple ways to ask questions like that. They can either say, give you a list of cations and anions and just elements and say, which two are isoelectronic? You got to do the electron configuration out for all of them and pick the ones that are the same. Or it can give you some sort of configuration and say, what are some possible choices of cations or anions or just an element that could fit that electron configuration. Okay? So, just wanted to bring that one to your attention. And then, here are these problems that, I know my recitations are sick of doing these with me, but I do them because this was the biggest, this is on your test the most. Stoichiometry. On your test, the absolute most. They didn't even give a number, they just said a lot. It's a lot of stoichiometry, right? So if you can do stoichiometry really well, you're at a big advantage right now, okay? So when we do stoichiometry, you guys, what happens is we're given some sort of equation. And what stoichiometry allows us to do is take the amount of reactants we're given